Last time we considered the average of multiple random variables, and we showed that if all of the random variables were identical in their expectation and in their variance, then we could easily come up with some properties for the expectation of the average, this new random variable, and the variance of the average, this new random variable. We found that the variance gets reduced when you take an average. Now, we also added the special condition that our random variables were normally distributed. Now, if they were normally distributed, it turned out that the average was also normally distributed. And as we said, the expectation would be the same, but the variance becomes reduced. Well, now we want to extend this. What if our random variables are not normally distributed? What if they are some other type of distribution? Or what if I don't know about the distribution? What can I say about the average? We will still have the case that regardless of the distribution of those random variables, we will still have that the mean behaves in that way, that it preserves the mean of the individual random variables and the variability gets reduced. But in this case, we do not know what the shape of that new random variable will be. Now, it turns out that there's a really important result. The central limit theorem tells us something about the shape of the average. Essentially, if all of these random variables are IID, and we happen to know that the means are given like this and the variances are given like this, then it will turn out that the central limit theorem gives us an amazing result. Then it says that the average is normally distributed with the mean and variance that we expect as the number of these independent random variables goes to infinity. Now, you may not appreciate what this is saying. It doesn't care what the xi's, what distribution they have. This is true for any xi's that are IID. It doesn't matter what. They could be unknown, they could be Poisson, they could be binomial, they could be normal, they could be exponential, it could be anything. And so the central limit theorem tells us that the average still obeys a normal distribution, but there's a bit of a kick here. We need n to go to infinity. So this is more of a theoretical statement, right? In the proof of this central limit theorem, there'll be a limit as n goes to infinity. Now, in practice, we can't have n going to infinity, okay? So in practice, it's usually sufficient to take n greater than or equal to 30. So the central limit theorem is amazing because it allows us to work with the average. So this random variable x bar, it allows us to work with it using a normal distribution. Now on the sheet that I've got, I have an example to do with insurance. So insurance companies are in the business of providing support if there's some sort of accident. But in order to stay in business, they realize that out of all the people that get insurance, they cannot pay every single person. They are betting that most people will not have any sort of, in this particular case, fire damage, but only a few will. So they will collect insurance fees based on that assumption, enough so that they make money and are able to cover all the losses of those people who need it. So in this example, we have that all of our xi's, so let's say x1 through to xn, they follow some unknown distribution. So we are going to assume that they are all IID. So that means we're going to assume they're independent, and we are going to assume they're identically distributed. So whatever this is, and we'll say that the xi is the amount lost by a policyholder or a homeowner in this particular case. So we don't know what distribution that follows. Maybe it's normal, maybe it's not. In fact, it shouldn't be, because the insurance company knows that it has to be strongly right skewed. So if this is the number of people and this is the amount that they have to pay out, it has to be the case that they pay actually, I should put this the other way. They have to pay very little to a lot of people. So they have to pay very, very little money to very, very many people. But then the amount of money should get larger as you go out this way, but there should be few people. So this is few people with a lot of money, and this is many people with little money. Now, all we know about these individuals is that the mean loss is $250 per individual, and the standard deviation is 1,000. So that means the variance would be 1,000 squared. Now, in order for this company to stay in business, let's say, for instance, that they do their calculations and that the average loss has to stay under $275. So let's say that the break-even point is $275. Now, this company does not just want to break even. They want to make money. And so they would like to know that if they consider 10,000 individuals, which is way bigger than 30, what's the probability that the average loss will be greater than $275? Okay. Now, if we need to calculate a probability, we need to know a probability distribution for the average as its own random variable. Well, we know that because n is really, really big here, the average will follow a normal distribution. Its mean will be 250, and the variance will be the variance of the individual variables divided by n. So if we want, we could simplify this down to 250 and 100. And this is in some ways so simple that we may not appreciate what the central limit theorem does. I don't know anything about the distribution of this monetary loss. I don't know what kind of random variable it is, but it doesn't matter. If I consider the average of it, I don't need to. The central limit theorem tells me it's normal. So then the question of calculating the probability whether or not this is greater than 275, I could just simply rewrite this as a CDF problem and ask what's the probability that it would be 1 minus less than 275. So I could go into R and use P norm, and I'd have 275. I'd have the mean of 250. And remember that P norm wants the standard deviation and not the variance. So this will end up being a very, very small number, 0.0062. So it's highly unlikely that the average monetary loss will be greater than $275. The central limit theorem is also useful for totals, not just averages. And what I mean by that is, by definition, this is essentially a sum of our random variables over n. So if you want, you could think of it as x1 plus x2 all the way down to xn divided by the number of observations. So if I wanted to, I could reorganize this and say n times the average would simply be the sum of all those individual random variables. This is the total amount. Now, by properties of expected value and variance, I know, look, that the expectation of an average, let's say that it's just this, and the variance of an average, let's say from earlier we discovered it was that. This is assuming that our xi's are all iid. But by further properties here, if I wanted to consider the expected value of nx bar, I know that I'm allowed to take it out, the n out, and just multiply it. So I'll get n times mu. And at the same time, I know that if I want to take the variance of this expression, I'm allowed to take that n, square it, put it outside, and multiply it by the variance of the average. So I'll get n squared sigma squared over n, which is n sigma squared. And so that means if I were just to call the total equal to some capital X, according to the central limit theorem, I know that x is simply nx bar. And I know from chapter 5.2, if I scale a normal variable, I still have a normal variable. So it's still a normal random variable. So according to central limit theorem, the average is a normal variable, and that means that the total will still be a random variable. It will just have a different mean and a different variance. So for instance, on the PDF sheet, I've got this example to do with apples. So suppose that 500 apples are ordered, and you know from past experience that the mean weight of each apple is given and its standard deviation as well. So what's the probability that a shipment of 500 apples is less than a certain amount? Okay, so let's say that xi is the mass of an apple, and we're going to assume that they're iid, and we're going to assume that I will go from 1 to 500. Now we know, we've been told, that the expectation of each xi is 0.2 kilograms, and that the variance of each xi is 0.1 squared. Now let capital X be the total mass of these 500 apples. X as n times the average here. And in our particular case, this would be 500 bunches of X. By the central limit theorem, because our n is 500, our n is very large, we know that x has to follow a normal, x bar, sorry, has to follow a normal distribution where it's 0.2 and 0.1 squared over 500. So 500 times this x bar. We can now say something about the probability distribution of this x bar. We know that it's going to be given by 500 times 0.2, 500 squared times 0.1 squared over 500. So just like I outlined a moment ago, this means I'm going to have 100 and then 500 times 0.01. And so in that sense, I know that this total is normally distributed with a mean of 100 and a variance of 5. And so, if I wanted to calculate the probability that the total will be less than 98, it becomes very straightforward to go ahead and do that. We can just simply use a p-norm calculation, 98, and we would use our values here, remembering that we always take the square root. And in this sense, using p-norm, it becomes very, very easy to calculate the probability. There's about a 18.5% chance that the total shipment will have a mass less than 98 kilograms.